Let's start a discussion on magnets with something that we probably already know. If we have a magnet, it has two ends. One's called the south end and the other's called the north end. And so there's these two ends, and if I were to break the magnet into two pieces, I come up with two new magnets. And if I can try to break them again, then I'm going to get two new magnets. North end, south end there, and then north end will go with south end. So magnets always have to have two ends, north and south. And much like we had with charges, with positive and negative charges, we have similar things happen with the positive or north and south side of a magnet. So if I take and put a north side pointing towards the north side, then I'm going to get repulsion. These two are going to repel. And if I put the south sides together, I'm going to get the same thing. I'm going to get repulsion. But if I put a north and a south together, now I'm going to get an attraction. Now there's this influence, much like we had with an electric field. A magnetic field has this field or influence around it. So if we look at a bar magnet, a south end, north end, there's this magnetic field that exists outside the magnet, but it also exists inside the magnet. And so this field rotates or curls around this magnet. And there's going to be a magnetic field this way, and more. So we know that with the electric field, is conservative. And that's because it starts at positive charges and ends at negative. But magnetic fields are not. They're non-conservative. And the reason is that the field lines don't terminate. They just keep going forever. Now there are scientists, if you ever watch Big Bang Theory, uh, they had episodes on this, but there are scientists that are looking for mono, or I should say magnetic monopoles. Monopoles. Monopoles, okay. And if you had magnetic monopoles, then the magnetic field would be conservative, but they've never been found. And so at this point, we do not think that they exist. People are searching for them, but we don't believe that they exist. Now, the Earth has a magnetic field, and if you look at the Earth's axis of rotation, so this is its rotation axis, the magnet actually sits at an angle. And that angle is called declination. And the angle at which the magnetic field exits or enters the Earth's surface is called dip. Okay, so now if I have a compass and the north side of my pointer points north, that means that the south pole of the magnet is at the north pole and the north pole of the magnet is in the south pole. That's the only way you can get that north needle pointing in the north direction. Now you'll find on topo maps they will have the map which tells you it'll have an arrow and it'll say true north, and then they'll have another arrow that says like magnetic north. And so on your compass you usually have a ring that you can move. This ring has angles on it. The map will tell you how many, could be like 10 degrees. It'll tell you how many degrees you need to compensate your compass so that you get to true north. And you can set your maps. Now, the interesting thing about this angle is that it's different on all topo maps. It's different in all locations of the Earth. So you have to look at the topo map to give you an indication of what angle you need to set your compass to be able to point to true north. So this is just the background of magnetic fields, and we'll be expanding this concept even more as we go through this chapter.